So we'll be covering Chapter 7 today, which is IP addressing, and kind of talking about what this is all about. I'll be covering primarily IPv4 and IPv6. I'll mention IPv5 because I think it's kind of funny, but it's not going to be on the exam or anything. So like I say, it's all about basic terminology, that sort of stuff associated with it. So this should be a review. Who can tell me what a bit is? 1 bit. What is a bit? That's right. 0 or 1. What's a byte? That's right. What about octet? What's the difference between a byte and an octet? Trick question. They're basically the same thing. Make sure you understand that. They're going to be used interchangeably in here. Technically speaking, they're not interchangeable. But this is not an advanced networking class, so don't worry too much about that. Of course, network address is going to be an address used to identify a host on a network. Pretty straightforward. IP address is going to be very similar. And then, of course, broadcast addresses are going to be wherever we basically just use a subnet mask to send out a message to every host on the network. I should have kind of cautioned that and say that you won't actually see the message as an end user. Did anyone get a chance to run Wireshark on their personal network or some similar packet capture utility? Like I said, I recommend you do it. I might throw it into one of the labs. We don't have a ton of time for labs, but just recommend you do it. It's kind of cool to see how this all sort of works and how it all fits together. So, talk a little bit about hierarchical addressing. So, and this is for IPv4 specifically. Each IPv4 address is going to be 32 bits. So, if we have 32 bits, we know it's going to be 4 octets. So, think about a traditional address. It can basically go up to 255, 255, 255, 255. Now, it's not technically true because they start at 0. Okay, so make sure you understand that because, of course, there's 255. So keep that in mind. The book talks about they're going to be represented by a decimal. I think it's perfectly okay to use our good friend a colon. I think colon's a little bit more readable. You can have your own opinion. Certainly I'm not telling you have to represent things via decimal or a colon. It's up to you to decide. However, make sure you're consistent. So maybe you're someone who prefers to use the period. Okay, don't mix and match periods and colons. Why not? Because it's confusing. So we can represent it via decimal. You've probably seen that quite frequently. If you really want to go a little bit crazy, you can certainly use binary to represent them. And of course, you can also use hexadecimal. So 3 different ways we can represent them. In this class, I would expect you to use decimal. Why would I expect you to use decimal? Are you a robot? Unless you're a robot, don't be using binary. A little bit of 8 a.m. humor there. So, like I say, we have hierarchical addressing, and basically what that means is that there's certain aspects of IP addresses that are going to be relevant to the individual host, and there are certain aspects of IP addresses that are going to help us get it to the relevant network. So, for example, the book uses these area code, local calling area, and customer number, talking about the different octets and what they mean in a public address. I wouldn't necessarily use these particular terms to describe them, but hey, they did, so we'll go with it. So basically, you have your area code, and that's basically saying in what general area is this. And the reason I wouldn't use it is because in modern time, we're talking about area codes. It has a lot different meaning in 2021 than it did in 1990s. Just given how the IP addresses have sort of been dispersed and sort of given out. So keep this in mind. It doesn't necessarily directly relate to a geographic area. In many cases it will, in many cases it won't. Okay, then the second octet's going to be for the local calling area. And then finally, third octet's going to be for the customer number. So like I say, I personally want to choose these, but just make sure you understand that, basically if you have some random IP address, let's just put 97.23.101. This is a made up address, don't code to it. Okay, saying this is going to be somewhere around the area that it is. Okay, then you've got your local area, so a little bit closer, a little bit more specific. Think about a map of the world. Think of 97 as being which country. Think of 23 as being which region or state. Okay, is it perfect? No. Like I say, we're going to talk about some of the various problems with IPv4. I'm going to disagree with the book a little bit and say that IPv4 is probably fine to use. The book says that you must convert everything to IPv6. I disagree with that. I think there are certainly ways we could continue to use IPv4. And I think if we look over history, does IPv4 work for 2021? Yeah. Will it work for 2030? Who wants to take a bet? I'm not actually going to bet. But who would bet that IPv4 will not work in 2030? Let's debate it. Who thinks it won't? Who thinks it will still work? All right, I agree. So who wants to disagree with me? Anyone at all? I disagree with myself. I'm certainly not above that. So, kind of thinking about the limited address space, there's only so much that network address tunneling and similar technologies will enable us to do to share IP addresses. There will become a time in which that won't be feasible. Now, is that accurate or inaccurate? I'd say it's very likely inaccurate. So let's talk a little bit about network addressing. Like I said, the book doesn't do a great job with this. They kind of just say, Class A is going to be, just using the first octet to distinguish the network. And then they say Class B is using the first two octets. And finally, Class C is using the first three octets. This is still kind of confusing. So if you read the book, you might be going, this is a little bit convoluted. But basically, so understand that the network address is going to uniquely identify the network. So we've got something called subnet mask, where we basically put 255 for everything that is not going to be unique. Okay, so for example, if we were using a Class A network, we would use something like, let's say, 26.255.255.255. Okay, and like I said, this is going to make a lot more sense once we kind of look at some better graphics. Okay, so like I said, Class A, you're going to be running from 1 to 126. And the reason for that is because the first digit is reserved. Okay, so basically it's going to support 16 million hosts. That's a fair amount on 127 separate networks. So hypothetically, you could have one network at, say, let's say it's at 1.255.255, so on. Then you have another one at 2, okay? And that's theoretically possible. However, when we're talking about would you be able to realistically provision those addresses, the answer is no, at least not following any sort of reasonable practices, because we have private addresses. So realistically, if we have one major network, it's going to be on the 10, and everything else is going to be reserved for hosts. So make sure you understand that private addressing is going to allow you to have basically the networks on that sort of way. And then of course, for home networks, you're probably going to use a Class C. Most of your home networks are probably using a 192 address. That's what you'd expect to see. But no requirements, nothing saying you can't use a Class A. Does anyone use a Class A on their home network? No requirements saying you can't, but most people choose not to. I'm going to disagree with the book a little bit when they say not to use a Class B in any sort of a corporate environment. I think there's a lot of cases in where you would want to use a Class B, particularly if you want to do a lot of segmentation. I think it may be a lot easier on Class B than Class A. It's an opinion. Feel free to disagree, but I certainly think it can be easier. I'm not saying you should, I'm just saying you can. Now obviously if you're supporting a network instance, let's say it's Walmart. Okay, how many hosts does Walmart have? Easily in the millions. Are you going to be supporting millions with Class B? Obviously not. But if you're just running a relatively small firm, say under 500 employees, I think Class B could make sense. I'm not saying it does, I'm just saying it could. Because let's face it, is it that hard to convert from Class B to Class A? Is it that difficult? Not really. So if you ever did expand very rapidly, you'd easily be able to transition over. Probably take you under a week. Okay? So yeah, make sure you understand that the different ranges, there's a public range and there's a private range. Make sure you understand that. Any questions about this? Something that's not on here that should be on here, we'll cover it in a couple slides, it's called IPv4, Automatic Private IP Addressing. And basically, that's going to be 169. I don't remember the exact, but it's going to start with 169. That's the first octet. And basically, that's going to be returned if you're able to communicate with a DHCP server to provision an IP address from the DHCP server. So whatever device you're on will go ahead and grant a pipe address. Most of the time, that's going to indicate that you're unable to communicate with the rest of the network because nothing's going to match. Okay, we're not going to go over this too much, but just basically I just want to kind of go over this a little bit. If you have a network address of all zeros, you're talking about one specific segment there. All ones is going to go out to everything. This is probably the most important one, 127.0.0.1. That's going to be localhost. So whatever device you're on, it's going to have a localhost address. That's going to be it. So hypothetically, you'd be able to test packet transmission, but it wouldn't be something that you'd use a ton. Just understand that's localhost. Yeah, and then the rest of it's pretty self-explanatory. You got a question?
Yeah, on the previous slide,
yeah.
When it says your address range, why do some of them only go to 254 rather than 255?
So where are you at? Right up here?
Yeah.
So a lot of times 255 will be reserved for multicast. So that's pretty much why. Any other questions? And like I said, there's a lot more reservations than we covered. Like I said, we didn't cover 169. Whatever, and of course IPv4. There's several others like that. Like I say, you don't necessarily need to know them for this class. You don't necessarily need to know them for really much of anything. Because for the most part, let's say you're a network engineer, okay, working for a big company. You're pretty much going to be sticking with one of these three. Most likely, you'll be sticking with Class A. Okay, so if you see something that doesn't start with a 10 or doesn't start with a 172 or a 192, then maybe you want to investigate a little bit further. But for the most part, just understand the first octet, and most things will just kind of work. Does that make sense? So, like I say, there's dozens of different reserved addresses. I don't think they're too important to memorize personally. IPv4 is important. Definitely the private addressing is important. And private addresses don't leave their router. Make sure you understand that. They're kind of like a MAC address where they're not going to leave your local network. Does that make sense? So a public address would leave the router. So, like I say, you can have one public address, and it's going to allow you to communicate externally. And then, of course, that one public address is that's what you use to communicate with parties outside the network. But then your router is going to be smart. It's going to have your private addresses, and that's how it's going to send packets out. All right, let's talk about virtual IP a little bit. Virtual IP is basically the same thing as network address translation, but it's for the destination specifically. So when you think about traditional central network address translation, we're talking about using a source. So, like I say, you're using destination for virtual IP. So don't worry too much about that. Just understand the basics there. Like I say, IPv4. If you don't receive an address from DHCP, you'll be granted IPv4. And like I said, here's the specific range, 169.254. So make sure you understand that. You'll probably see at least one test question about IPv4. But like I said, I'm not going to ask you about some random reserved addresses. Just make sure you understand A5. Okay, so you have layer 2 broadcast. Layer 2 broadcast is where you're going to send everything out to the local area network. So specifically, whatever's on that specific collision domain will receive a broadcast. And layer 3 is going to send it out to the entire network. So one example of that could be like an ARP request, trying to figure out what someone's address is based on their MAC or that sort of thing. So does that make sense to everyone? All right, then of course we have unicast versus multicast. It's enabled to imply unicast is going to go to one device. So if you're sending some packet, it's going to be a unicast transmission. It's going to one single host. Okay. In contrast, multicast goes to many hosts. Does it have to go to every host? No. But it can. It just doesn't have to. So you can kind of specify where exactly it's going to go. All right. IPv5. You guys ever wonder why we go from IPv4 to IPv6? I did too. So I looked it up. It turns out it was an actual thing. It was primarily used for streaming protocol. And basically it still used the same 32-bit address scheme as IPv4. And because it's using the same 32-bit address scheme, does it really provide any major advantages? Not really. You can make an argument that it does for streaming. I would personally argue against that. But like I said, it's an opinion. Feel free to argue if you want. I'm always down for a good, healthy debate. Like I said, it's not going to be on the exam. No one really talks about it. Just understand it's something that was developed and never really caught on for obvious reasons. They basically copied and pasted IPv4, added a little bit of stuff to make it better for streaming. Something that is relevant is IPv6, and like I say, I personally disagree with the book saying that it's absolutely necessary everyone move to IPv6. I don't think it is. I think existing networking technology is able to support modern applications just fine. Having said that, it does have some advantages. So the obvious advantage, there's a lot more addresses. Can anyone read this number right here? Well, I can't either, but it's a big number. We're talking about 4.3 billion addresses for IPv4 to substantially more than that for IPv6. Like I said, I'm not going to ask you how many more, because that's a ridiculous question. There's no need to know that. Just understand this is going to be ample addresses for quite a while. Now here's a good question to debate. Do you guys think we'll ever run out of IPv6 addresses? Let's debate it. Who thinks we will? Who thinks we never will? I actually think we probably will at some point. Now here's why I think that, before you call me a smooth brain or anything like that. Part of how we derive an IPv6 address, part of it is often from the MAC address. Okay? And our MAC address is finite or infinite? They're pretty finite. If you think about the unique part of them, it's really only the last 6 characters. So we got 6 hex characters. That's really all that we have that's unique. Now, having said that, could we find ways around that with current IPv6 technology? Yeah, we could. There's a lot of ways around it. The main one being to add on additional sort of information. That's part of what we do already. But I think it's very feasible that we could run out of IPv6 just as we theoretically run out of IPv4. Now, obviously, if we think about in modern time, so 4.3 billion theoretical addresses. We know a lot of those are reserved. Let's just say there's 4 billion. I think there's fewer than that, IPv4. Are there more than 4 billion internet-capable devices in the world? I think so. Don't have the exact count, but I think it's pretty fair to say there's probably more than 4 billion. But it doesn't matter, because we have things like network address translation that allow us to basically share a public IP. So Having said that, there's some overhead to that process. You know, it's not going to be 100% fast. Having said that, would that be more or less of a problem in 2021 for most places? So we have network address translation. It has some overhead associated with it. Like I said, the packets are going to be bigger than IPv6. Is that going to be something that is going to be more of a problem in 2021? Or would it be more of a problem in, say, 2005? I would agree with 5 because network speeds across the board, I mean, for the most part, pretty fast in most places. I unfortunately do not get fast internet where I am. Hopefully that'll change. You guys see that Starlink is going out of beta next month? Won't that be cool? I hope I finally get my pre-order. We'll see. So again, just understand that we're talking about there's still some address constraints even with IPv6, because in reality, are we going to see anywhere near this number of usable addresses? No. So, to me, I don't see it as being something that's going to solve all the world's problems. Personal opinion. It's okay to disagree. A lot of people do think it will. I just look at the information available, and I personally don't think it will. One advantage has IPsec built into the standard. So basically it's going to encrypt the packet. Not the packet though, more like the header. So to me, you can do that other ways with IPv4. I don't consider it a huge advantage. Mobility, this is something that's pretty cool. So if you're switching from one network to another, traditionally, obviously any connection that you had established would need to go away. Or cease to be a connection, let's say that. But basically with mobility, because most of the address is coming from MAC address, you can basically keep a lot of those connections established between networks. Now, having said that, let's say you have like an hour flight time and you hop back on a network. Are your connections still going to be there with IPv6? Probably not. Most things are going to time out eventually. So we're talking like a couple seconds. We're not talking days and days and days of not being connected. Does that make sense? Let's make sure you understand that. Smaller headers, that's probably the biggest advantage in my opinion, because if you think about an IPv4 header, it's pretty big, isn't it? So you guys remember the difference between TCP and UDP? Which one was Chad? Exactly. So think of this as being kind of like UDP in terms of having a smaller header. It's actually a little bit bigger than a UDP header, but just make sure you understand that. And obviously, of course, we're going to use 128-bit addresses. So for that 128-bit address, it's going to be comprised of 8 16-bit hex colon delimited blocks. So here's one example. You can see it's got 8 different hex blocks there. So could anyone memorize this? It's another disadvantage. It's a lot more easy to memorize IPv4. I mean, I've probably got a couple dozen IPv4 addresses memorized. Ask me how many IPv6 addresses I have memorized. The answer will be 0. Okay? But there's some tricks we can use for them. We'll get to that in a little bit. Just a little bit about the different address types. Just like with IPv4, unicast goes to a single place. Global unicast is going to be publicly routable and going to a single place. So there's less of a concept of having public versus private IPv6 addresses. I'm not saying it doesn't exist, I'm saying it's less of a thing. So a lot of them are going to be publicly routable. And of course we also have link local. And these are going to be basically the same thing as a private address. The book says they're like an APIPA address. I disagree with that. APIPA addresses, generally speaking, are not going to be usable for network communication, whereas a link local address will. So I personally disagree with the book a little bit there, but like I said, feel free to have your own opinions. I'm not telling you what to believe. So unique local address, this is where we're going to have things that are going to be very unlikely to overlap. And why is that? like I say, if they're coming from a MAC address, that's one of the main ways they're derived, then we know that MAC addresses are unlikely to overlap. Ergo, we can determine that something using a MAC address is also going to be unlikely to overlap. Of course, we have multicast. Send something out to multicast instead of using 255. You're going to use FF. Why would you use FF? Well, because it's basically the highest it can be. Just make sure you understand that. And then lastly, anycast is going to go to the closest address. I use closest very loosely. It's not really going to the physically closest. It's going to whichever host it can reach first. So just make sure you understand that. Yeah, we're not going to worry too much about this in here. What we will worry about, though, just kind of understanding this stateless auto configuration process. This is probably the most important part of IPv6, just understanding how specifically each of the hosts are going to be derived. So what they're going to do is they're going to sort of address themselves in a lot of cases. Now, does that mean we can't use DHCP? No, it doesn't mean that at all. We still can, and in some cases we would. There's not every case in which we would, but we could. It's something we're physically able to do. But basically what's going to happen is your device is going to contact the router, get its prefix, and it's going to append its MAC to it. So this is going to go on the 7th bit basically, and like I say, you have your OUI, which can be that thing that's unique to the manufacturer, and you have the unique address, which is going to be unique to the device, and we're going to put FF and FE on the end and beginning of those two things. So for OUI, to fill out the entire 64-bit, put the FF. To fill out the 64-bit for the unique address, put FE. Does that make sense? And this is done automatically, like I said. It's not necessarily DHCP. We can still do DHCP though. So there's one or two reasons why you would, especially on an enterprise network. So for example, let's say you had a DNS server that you wanted to assign. You could do that at the router level. You don't have to do that. You could also do that at the device level. But if you want to do it at the DHCP level, you can. So basically all it's going to do is auto configuration plus a few other things. So nothing really groundbreaking here with DHCP v6, but just understand that it exists. Okay. One thing we haven't covered, do I have slides for it? Looks like I do not. No, that's okay, we'll cover it. So dual stacking is going to allow us to basically support on one router either IPv6 or IPv4 transmission. And then 6-to-4 tunneling is basically going to create a tunnel that's going to go across an IPv4 connection. And it's basically just going to have the IPv6 addresses inside of them. It's basically what it looks like. You got your host network, you got your router, supports dual stack. You're going across an IPv4 network, you got another router on the other end that supports dual stack, and you have IPv6. What's the reason for doing this? Is there any advantage to this? So, the only reason I could think of why you would do something like this is if you're in the process of migrating and you're actively doing it. So just make sure you understand that. This is stuff from last unit I forgot to remove, I guess. I must not have saved the latest version of the slides. Anyway, not a big deal. The only thing that's not in them is about how we can sort of shorten these addresses. So let's go back to them. So this address right here. Okay, there's a couple rules. Make sure you know these rules. Like I say, you'll definitely see this on the exam. Any leading zeros you can omit. So you can omit any leading zeros. In addition, you can also choose to omit one continuous block of zeros. So for example, this right here, starting for the 0, ending right here, you can omit that. And when you omit that, use a double colon. Now you can't do that twice. The reason you can't do that twice is if you omit 2 of these and they're not continuous, how do you know how many blocks of zeros are in each space? Do you know that? You can't determine it. That's why you can only do 1. So let's just go ahead and draw this out on the board here. So for the first step, I would take 2001. Okay, then I could do DB8. 3C 4D. Okay, I can do 12. And like I said, the first step, I'm just going to put a 0. 1, 2, 3, 4. And then 5, 6, 8, B. And like I said, for the second step, we can just remove these two zeros. So I'm just going to be a little bit smart here. And basically, we're just going to put a double colon to remove those. So you just wouldn't see those. Does that make sense? All right. Any questions? Like I said, just make sure you understand IPv6, make sure you understand IPv4, and that's really all there is to it. Have a good day, everyone.